time to talk gravity and the law of universal gravitation, brought to you by our friend Isaac Newton, with a little bit of help from a guy named Lord Henry Cavendish, who we're going to talk about in just a little bit. So we're going to talk about what this value, what this gravitational field is, when we've been talking all this time about gravity pulling things down towards the center of the earth. We talk about forces and things of that nature. We're going to try to put some more thought and kind of nail this topic down a little bit. And the best way to do it is to talk about some of the equations that are associated with that, and use it to calculate some things. And you kind of come up with some really good values if you do the right calculations, and you see sort of how everything sort of works together. So we know, or what do we know about gravity? And I'm going to start off by saying that you guys are going to learn a little bit more about this next class, is that gravity, even though we know that it does work, we can describe and throw a whole bunch of math on it to make predictions about the behavior of certain objects when they're under the influence of gravity. We know a ton about that. We can do all those calculations. We know all of those things. But one of the things that gravity is one of those things that we don't fully 100% understand. We're getting a little bit, and when I mean understand, I mean truly understand that there is something out there that just by having mass alone, it produces this field that can impact other masses. So anything that has mass has a gravitational field around it. Scientists are working really hard to truly understand what that actually means. And so if you're feeling a little lost about this and saying, okay, well, I don't really totally understand what's going on with gravity, even though I've done all these calculations, like I know how to work the calculations, but I don't really know what it means, that's okay. If you can describe the relationship, you're right on par. The relationship of how gravity, or the force of gravity in a gravitational field, might change the way that matter behaves, you're in good shape, because that's right about where we are right now anyway. So what do we automatically know about gravity? Well, we know it's one of the four fundamental forces, if you remember from your chemistry days. It's the weakest of all four fundamental forces, and if you think about it, that makes sense. You've got, in order for us to escape the gravitational field of Earth, we just got to launch a rocket fast enough. So that can't really be said for something like the strong nuclear force. So gravity is definitely the weakest of all of the fundamental forces, even though we see it the most frequently, because obviously if we were not under the influence of gravity, we'd be floating away right now, and we're not. So it's the one fundamental force that's in our face the most, but it's because it acts on objects that are all objects, but we notice it the most when it acts on objects that are larger. So we do know that the force of gravity does act between all masses. And so that's why we call it universal gravitation. This is, for what we know, this is this idea that two masses will have some sort of gravitational attraction to each other. We know that that occurs everywhere. That idea of the force of gravity never really reaching zero, that is a concept that is a little bit tough to get your brain around if you think about it. That value is going to obviously decrease. We're going to talk about that relationship in just a second with that increasing distance. So the more space you get between two objects, the less that gravitational field has an effect on an object. But the idea that it never quite goes to zero is kind of an interesting thought. If you think of the size of the universe and how far some of those stars are away from us, and the idea that gravitation does still exist. It never officially drops to zero. It does get really small, and it can get to the point where we call it negligible, which might show up on a test. Showing that the force of the Earth somewhere might be negligible someplace. The gravitational field of the Earth might be negligible somewhere else. That might show up on a test. I don't know. I just write them. So what we do know is that the size of that gravitational force between two masses is going to increase with increasing mass. So in other words, the larger the mass is, the greater the gravitational field strength it has. But the further away those objects are, the lesser the gravity is between, or the lesser the force of gravity is between those two masses. So if we want to take a look at these, look at that gravitational force separately, we can say that force is proportional to the big mass times the small mass. I'm going to cover this up because we're going to get to that in just one second. That little fishy is proportional, means proportional to. And it's inversely proportional to the distance between. So we're using r because radius is a lot more of a friendly value as we work through a lot of these problems. So when we combine these two equations together to take a look at what that relationship is, you can kind of see where this is headed. We get the equation that the force of gravity between any two objects is equal to, whoa, where did that big G come from? What is that? We're going to talk about that in just one second. This is G, and that is the mass of the first object, the big object, times the mass of the smaller object divided by that radius squared. So that's our big equation that we're going to be working with over the next couple of days. So F is equal to GMM divided by R squared. Well, what is that big G? That big G is the universal gravitational constant. That value is 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared. It's kind of a funky unit, but as you guys know or have experienced in your chemistry classes, that anytime you get a constant, usually the units are kind of jacked. So the guy who discovered this is somebody named Lord Henry Cavendish. He also just so happens to be the same guy who discovered hydrogen. So he kind of knows his stuff. He also, in earth science land, he was the one who calculated the density of the earth. And by default, also calculated the mass of the earth. So this guy, this Lord Henry Cavendish, was pretty wicked smart. He discovered this gravitational constant in 1798. So just for some perspective, Mississippi was just becoming a territory in 1798 while this was getting figured out. And Napoleon was kind of on his rampage over in Egypt while this was all occurring. So, you know, we got wars going on between Napoleon and Egypt, and there's Lord Henry Cavendish just, you know, chilling, calculating some gravitational constants. Lord Henry, you want to go to war? No, I'm good. I'm just going to calculate this universal gravitational constant here. But he managed to do it. He was also really precise scientist. He did a really good job of making sure that he eliminated any possibilities of error in his calculations. And his first calculation that he came up with, or the value that he got for G, was something like 6.65. So that was back in 1798, pretty darn good. So, you know, not only is he discovering hydrogen, he's also figuring out this universal gravitational constant between two masses. So just want to point out to you guys that I highlighted this negative 11 here because this number is so small. It just kind of highlights that concept of that force of gravity being one of the weakest fundamental forces. We're multiplying every single one of our problems when we're looking at the relationship or that force of gravity between those two masses by a really tiny number. And then we're dividing it by a number that, as that number gets bigger, then you're dividing by a much larger number. And so this number goes down pretty darn quick. So let's take a look at an example of that. I'm going to have you guys maybe hit pause and try this on your own first. It's going to kind of step you through and combine some of the things that we've been talking about centripetal with centripetal acceleration and things like that, and just sort of working gravity into it. But before you hit pause and work this on your own, I forgot something in the notes. The period of the moon around the Earth for this particular problem. So the moon's period is 27.3 days. Okay, so that's one little tidbit that I forgot to put in there if you want to try this problem on your own. So my suggestion to you is that you hit pause, try to work out A, B, and C, and then see what you come up with and see where you land. When you get to part C, I'm going to talk a little bit more about that. You're going to be like, why am I comparing this to G is divided by 60 squared for part B? Why do I compare those two numbers? We'll talk about that in just a second. I haven't really talked about it with you just yet. So hit pause. Let's get these numbers kind of hammered out and let's see how well we do. And I'm going to walk you through them. All right, so let's see how we did. So it says to calculate the average orbital speed of the moon. So this goes back to our circular motion. So it's a quick review. If you guys remember that one of the ways to calculate the velocity or the orbital speed around something is to take our 2 pi r, which is our distance, right? 2 pi r circumference, divided by the time, which is our period. So if we just start plugging in our numbers, we can take 2 times pi times the radius. So that's our average distance between the Earth and the moon. If we want to draw out what we're looking at here, we can say, okay, here's Earth, la, 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 and here's the moon. And a little, oh, you can't see that. There we go. So a little heads up for this, comparing this answer here. The distance between the Earth and the moon, Isaac Newton discovered, was about 60 Earth radii. So that is why we were going to be comparing our answer from part B to 260 or 2g over 60 squared. So if we can compare it and that number, that value is really close, we realize that that centripetal acceleration of the moon towards the earth compared to that g value divided by 60 squared divided by that earth radii is gonna come pretty darn close. So looking at our radius, that our distance actually becomes our radius, because as this moon does its thing, and travels around, that becomes the radius if we kind of take this in a whole circle, which I'm not going to do because I can't zoom the camera out that far. So, but you get the idea. So that becomes our radius. So our radius is 384,000 kilometers. We got to get that into scientific notation. Looking at the average speed, we got to get that in meters per second. So kilometers is not going to play nicely with us. We got to convert our kilometers into meters. So when we do that, we wind up with 3.84 times 10 to the 8th. So if you did just 384,000 and you did all that math and you hammered it all out and you feel like you got a good answer, and then you're like, shoot, I made that error, go back, recalculate, see how you're doing. So once you did that with the new calculations, now see if you're correct. So we're going to divide that by the period. Now we can't just divide it by 27.3 because 27.3 is in days and it's asking for the orbital speed, and we need to measure that in meters per second. Thank you very much, IB. So we need to do a quick conversion. So we're going to go 27.3 days times 24 hours in a day times 3,600 seconds in an hour, and that gets us to our seconds. The value that we get for this is 1.02, once we hammer that out in the calculator, times 10 to the third meters per second. This is one of the big arguments of flat earthers, by the way. I'm just going to get on my soapbox for a minute. That how is it possible for us to all stay on the earth if the earth, or if the planet is orbiting at this outrageous speed and is accelerating, and they start throwing in accelerations where they don't belong and all that good stuff. It makes me mad, and it makes me stay up late proving people wrong on the internet. So just good thing to know and tell. So 1.02 times 10 to the third means that the moon is moving around the earth, around our earth at about 1,020 meters per second. So she's going at a pretty good clip, team. So if we take that value and we try to calculate what the centripetal acceleration is of the moon towards the earth, that is an easy squeezy calculation. A centripetal, you did plenty of this when you did the PIGS lab, v squared over r. So we just plug that in, that value, 1.02 times 10 to the third squared, divided by the radius, which is again 3.84 times 10 to the 8th. The value that we come up with is 2.71 times 10 to the minus third meters per second squared. And so that's our acceleration, or a centripetal acceleration of the moon towards the earth. If we take that value and we put g in over 60 squared, that value comes out to be 2.73 times 10 to the minus third. So if you look, those values are really stinking close. Whoops, you can't see that. There we go. Those values are really stinking close. So you've got Isaac Newton on your side for that equation, basically, or for his calculations. So taking a look at Newton's law of gravitation, what Isaac Newton says, or his law of gravitation, which is going to show up on the test, and I'm going to highlight a really important aspect of that, is that the forces acting between two masses, two point masses, big M and little m, kind of makes me hungry for chocolate, are proportional to the product of the masses and inversely proportional to their separation, so how far apart they are from one another. We're going to call that a radius squared. So as I mentioned before, that just to kind of put that equation back in, F is equal to big G, that fundamental constant, M times M over R squared, knowing that there is a difference between capital G and little g. So our capital G is the fundamental constant. That is a fundamental constant. It's the same everywhere. So that means it's the same everywhere in the universe. And little g is that value for what we call gravitational field strength. And remember, I started using that word for you guys back when we started doing forces. And I said gravitational field strength is a better way to talk about it. It's just that strength of that field of gravity from one particular mass. So this force of gravity, is going to vary by location. And we're going to talk about that in just a second. So what is it that makes these two values different? Is that one is a fundamental constant, same everywhere. This one changes depending on what planet you're on, or what moon, or what asteroid, or what satellite, or whatever. It's always going to be dependent. It's that gravitational field strength of an individual object. So when we talk about this idea of point masses, and I want to highlight that IB really likes that you use these two words in this description when you get asked, because there's kind of some weird assumptions that happen with planets and things like that when we start talking about gravitational attraction between planets. And that idea is that these planets all kind of have varying densities wherever you are. So they make the assumption that you've got the same density everywhere. And then on top of that, that you're looking at that point mass is taking a look at that very center of that planet. So if you want to take a look at, say, for example, the gravitational attraction between you and the Earth, I suggest you actually use this equation to try to figure that out. Make the mass of the Earth the big M, make your mass in kilograms a little m, and then if you divide that, your radius squared, you're like, but I'm at the surface of the Earth, so the distance is 0. No, it's because we're talking about that center value. So we have to use the radius of the Earth in that situation. And then when you multiply that by g, you're actually going to get your weight in newtons. If you divide, in other words, if you divide it by 9.8, or if you divide your, if you reverse that equation back out again, you wind up getting 9.8. So it's kind of a handy way to do it. I'm going to show you guys an example of that in just a minute. So if you're like, wait, what? We're going to do some more with that in just a minute. Just the big idea that I want you guys to know for this particular video, there is a big difference between these two. And if we want to talk about the force of attraction between any two objects, this is our equation that we use. Okay, moving on to the next video.